The manufacturing process begins with the front glass, which forms the protective outer surface of the solar module. Each module uses specialized high-transparency solar glass, designed to allow maximum sunlight to pass through while protecting the solar cells beneath it. Unlike conventional glass, this material must be extremely pure. Even microscopic metallic particles embedded in the glass can scatter incoming light and reduce the efficiency of the panel. Before entering production, each sheet of glass is automatically inspected. The loading system performs a controlled bending test, applying a small amount of flex to verify the structural integrity of the glass and ensure it will not crack during the manufacturing process. Glass is the largest structural component of the solar panel. A completed panel typically weighs between 75 and 80 pounds, with about 3/4 of that weight coming from the glass layers alone. Once the glass passes inspection, automated handlers place it onto the production conveyor, where it begins its journey down the manufacturing line. Next, the process moves to the stringer machines, where the solar cells are electrically connected. Solar cells are made from crystalline silicon, a semiconductor capable of converting sunlight into electrical current through the photovoltaic effect. Inside the stringer machines, thin conductive ribbons connect the cells together in precise sequences, forming long electrical chains known as cell strings. These strings will eventually make up the electrical core of the solar module, or what you might know as a solar panel. The machines operate with both speed and precision, assembling more than 70 solar cells per minute while maintaining alignment tolerances measured in fractions of a millimeter. Copper plays a critical role in this stage because it is one of the most effective conductors of electricity. The United States also has a significant supply of this resource, with estimated copper reserves exceeding 48 trillion tons located in states such as Arizona, Nevada, Minnesota, and Utah. Looking ahead, T1 Energy expects to produce solar cells domestically at a fab in Rockdale, Texas, helping expand the U.S. solar manufacturing supply chain. At this point, and several more times in the future, the modules are subjected to rigorous inspection by both humans and machines. Once the cells are connected into strings, they move forward to become part of the module structure. Stage 3, layer assembly. With the solar cells connected, the next step is assembling the layers that form the solar module. A finished module consists of 5 primary layers: front glass, EVA Encapsulant Film, solar cell strings, a second EVA encapsulant layer, and backside glass. EVA, or ethylene vinyl acetate, is a specialized polymer film that acts as both a bonding material and a protective barrier for the solar cells. Across the facility, much of this assembly is performed by automation. In total, the factory operates 192 robotic arms that help position and assemble components throughout the production line. These robots place the connected solar cell strings onto the module with extremely high precision, ensuring the cells are aligned correctly and spaced evenly across the panel surface. By combining robotics and automated conveyors, the factory can maintain consistent placement while handling delicate materials at high speed. Once the layers are assembled, the module moves forward for permanent bonding. The layered module now enters the lamination stage, where the components are bonded into a single structure. The module stack is transferred into large industrial laminators, essentially high-capacity ovens designed specifically for solar manufacturing. Inside the laminator, the module is subjected to controlled heat and vacuum pressure. As temperatures rise, the EVA films melt and flow between the solar cells and glass surfaces. This process removes trapped air and creates a uniform bond between all 5 layers. At the G1 facility, the lamination system processes modules in batches. Each lamination cycle takes approximately 17 minutes, producing fully sealed panels expected to withstand decades of outdoor operation. When the module exits the laminator, the core structure of the solar panel is complete. After lamination, the module moves to the framing and electrical integration stage. First, a structural frame is installed around the perimeter of the panel. Frames provide mechanical strength, allowing the module to withstand wind loads, transportation stress, and long-term environmental exposure. At this facility, the company is transitioning toward American-manufactured steel frames, increasing the amount of domestically sourced material used in the module. A specialized silicone sealant is also applied during assembly. This sealant protects the panel from moisture intrusion so that if everything is working as expected, it can continue to generate electricity for decades. Next, the module receives its junction box, commonly known as the J-box. This component houses the electrical terminals that allow the panel to connect to other modules in a solar array. Robotics systems install the junction boxes with consistent placement and precision, ensuring reliable electrical connections for each module. Before leaving the factory, every solar module undergoes a final round of inspection, testing, and classification. At this stage, human technicians and automated systems verify that each panel meets both visual and electrical quality standards. Edges are finished, surfaces are checked, and the completed module is prepared for performance validation. One of the most important evaluations is the IV test, where the module's current and voltage are measured under controlled conditions. Often referred to as an artificial sun test, this process determines how much electrical power the panel can actually produce. That output is measured in watts, and the results are used to sort the modules into performance categories. This ensures customers receive panels rated accurately by their power output. Once testing is complete, the modules move to the final step: sorting, packing, and shipping. From there, they leave the G1 facility ready for solar installations around the world.